problems. Let's finish the last two. Yeah, let's try. If we finish the last two, yeah, I'll see if we can find a harder problem. So let P be any point inside ABC. And then we draw the orthocenters of PAB and PAC. All right. So for now, I'll just kind of do it. Let me do this. HC B PAC4. Oh, can I not? I guess I can't. It's off the screen. There we go. Maybe move P around a little bit. I guess that looks okay. And then we see where PA cuts the circumcircle of BPC. Whoops, sorry. That looks pretty nice. I like that. So this is point Q. And H is the projection of Q onto BC. Whoops. And we want to show AH is perpendicular to HBHC. So this kind of reminds me of the pond slip point. It almost looks like they're collinear, but I don't think that's true. Oh, does this look like IMO 2020? Oh, combinatorial GEO. I tried just to do synthetic on the channel just because there's like a lot of writing and special cases often and combinatorics. I just prefer, like, the goal for my channel is just to do mostly synthetic. Thanks for the suggestion. Let's see. Are these collinear? Okay, so interesting. Okay, so HB is the orthocenter of APC. That means P is the orthocenter of AHBC, right? So P is the orthocenter of two different triangles, right? P is the orthocenter of that triangle and this triangle. P is a double orthocenter. And BHC is parallel to CHB. Yeah. Interesting. 3B, 1B, Putnam problem. Yeah, you can post combinatorial GEO on the Discord channel, but for YouTube, I guess I prefer synthetic problems. Yeah, that's just sort of, I guess, my preference for the channel.
I think we can use that the perpendicular from A to BC.
Okay.
Because it is perpendicular to BC and AH is perpendicular to HBHC.
Okay.
Can be useful.
All right. You want me to let it meet the circle, or just
No,
draw?
just BC.
Okay.
I think AHQD is similar to BHC CHB.
BHCCHB. So the whole quadrilateral, you mean? AHQD?
Is HBC parallel to BHC?
I'm sorry, say that one more time. I apologize.
HBC and BHC. They are parallel, right? Because P is the orthocenter.
Yeah, BHC and CHB are parallel.
So I claim that BHC CHB is similar to AHQDA, AHQD, but I'm not sure.
No, this looks like a much thinner quadrilateral, I guess.
I realized that.
It's all right.
But maybe we can let AD cut the circle, so they can be actually there.
Okay.
They seem.
Do you want to draw both points?
No, they are not okay. They don't seem similar.
Mm-hmm. Let's see. All right. Yeah, I wonder if I wonder if we could do this with like spiral similarities. So P is the orthocenter of two different triangles. The orthocenter of this one, and it's also the orthocenter of that one. So yeah, maybe we could do stuff with homotheties, because this is the reflection of P over BHC, and if we extended it, this would be the reflection of P over HBC. See you, Hakan. Take it. Thanks for joining us. And see you, Yash. All right. So I see Sai joined. Oh, you sent it to Yash. My bad. All right. So one sec, guys. I'll be right back. All right. Thanks for waiting. Let's see. How do we do this? Yeah, so if we have two different, if P is the orthocenter of both this and this, it almost feels like yeah, I'm trying to think how we could use that. Maybe we could use Pythagoras, like we could show AHB squared minus AHC squared is HBH squared minus, because we have so many different perpendiculars that it seems like Pythagoras might help. Let me try something. Yeah, how would I get HBH squared and HCH squared? That would be kind of tricky. So HBH squared, that's like, so we could try to take in so HB squared minus, I'm trying to think about the power of HB with respect to this circle, is HBH squared minus the radius squared. And then we could probably do the same thing. It almost looks like HC lies on this circle, but I don't want to make it look like that. That's better. So that would be like the difference between the power of HB with respect to this circle and the power of HC with respect to that circle. I wonder if that helps. Oh no, H isn't the center of the circle. My bad. So that would not work. I don't know if it's worth drawing these points, or I'll just hide it for now. I wonder if we could do stuff with isogonal conjugates. It's an interesting problem. Have you guys heard of the Pon-Flit point? I think, let me try drawing the orthocenter of PBC. I'm gonna see. I thought there was something about this configuration where you draw the three orthocenters. I don't remember what it was. There's some fact about these three orthocenters. I don't know if it's like a, let's see. That almost looks like it passes through the foot of the altitude. Let me check it for the others. I don't think so. No. So yeah, I wonder if there's some relationship between P, HA, HC, and HB. Okay, I'm going to erase this in just a second. I'm just playing around with stuff for now. Yeah, I don't remember what that connection is. So yeah, we have a bunch of cyclic quadrilaterals here. I don't know if it's worth drawing them, but QEHC is cyclic. And QH, do we have like a Simpson line? It looks sort of like a Simpson line, but. Maybe I could try drawing the circumcircles of APC and APB. I know we're drawing a lot here. If I did that, are these concurrent? No. But basically, if we reflect HC over AB, it lies on the circle, and if we reflect HB over P, then it lies on this circle. So we kind of have a parallelogram. This looks like are A, B, E, and HC cyclic? No, I don't think so. I think that would be surprising. Yeah. Wait. Oh, yeah, because E doesn't lie on that circle. So yeah, they're not cyclic. But we could form a parallelogram here. So if you reflect HC over AB, it lies on this circle. And if you reflect HB over AC, And then it lies on this circle. Sorry, the diagram's getting kind of messy. And then, let me try. Oh, no, we have two parallelograms, AG, BHC, and I don't know how much this really helps, but it might. It reminds me of another problem we did. But we have, wait, what's the other one? So if you reflect HB over AHC, I don't think I drew point I right, actually. Yeah, I drew BP instead of HBP. So yeah, so yeah, we have like two parallelograms. I don't know how much this helps. Although this is weird. Something doesn't look right here. No, that's right. Oh, it's not a parallelogram, it's a kite. So AHBCI is a kite. So it might just not do very much. I think the point that makes a parallelogram would also lie on this circle, though. So yeah, well, you know what? Yeah, let me, what if I do this? So I draw the parallel through A. Because yeah, if I draw the parallel through A to both those lines, so, and I let it meet at 2 points, then we basically have two different parallelograms, right? So this is a parallelogram, and this is also a parallelogram. So that's one parallelogram, and that's another parallelogram. Whoops, should be this. And let me delete, I don't know if I need these circles right here. So yeah, so this is a right angle right here, GAP. These are both right angles. So yeah, so it's like I have the circumcircle of APB and the circumcircle of APC, and then I draw the perpendicular to AP. So I have these two quadrilaterals. I think that could be useful. I'm not 100% sure, but this looks so much like a problem I did. Do you guys see that problem on my channel where I did like the polar shape? I think the video is titled like a brilliant polar chase. But I think it was like a very similar idea to this. Okay. Yeah, I'm going to move on to the next problem. This one looks kind of hard. Then we could see if we end up solving that. Yeah, this one I think looks maybe a little bit easier. So we have the circle of ABC. Let D and E be 2 points on AC and AB. So there's a lot of sort of flexibility in the configuration. So we let BD and CE intersect the circle. A, and the other point is L. And the tangents at B and C, so maybe some medians, harmonic quadrilaterals, but they intersect the line DE at points P and Q. And so this is P, and we want to show that PL and QK intersect on the circle. It feels easy. It feels like it's maybe just like harmonic quadrilaterals or something, but we'll see. So let me make it so that we can see this intersection point. And let me hide some stuff. Maybe you guys have already solved it. I don't know. But let's see. ABE. Oh, it might be.
It seems the tangency problem we did.
Oh, it's like the same idea.
What Hakan said is true. Now we can do the same thing.
Okay, let's see. So,
it's not true.
Oh, it's almost true, but it's not. Let's see. Okay, so basically, we want to say something about the angle between PL and QK, right? That looks nice. All right.
Can you just draw the one of them, for example, PL?
Yeah.
And let it intersect the circle.
Yes.
Now can you draw AG, BC, and PQ?
Okay. AG, BC.
BC and PQ.
Ah, nice. So they
Pascal.
So by Pascal's they concur.
Yeah.
Yeah. AG and BC. Yeah, it's like the same idea. Okay. Well, first. So AG and BC, GL and BB, and AB and CL. And
We can prove from Pascal in 2 parts. First, we will prove that HPE are collinear. Then we will prove that similarly HPD.
okay, so HPE, I see that they're collinear by Pascal. HP and E makes sense to me. HP and D, is it the same argument? Or would it be, but I guess, are you sure we can apply the same argument to show HP and D are collinear?
I'm not sure.
Okay. Let's see. So did Hakan if we can Pascal AGK BCC. So yeah, I think we can show H. We can show H, P, and E are collinear, and we can show Q, and we can show H, Q, and D are collinear. But yeah, that's still, we want to show all four are collinear. So yeah, H, P, and E are collinear. So yeah, basically HPE,
Can you draw the line, delete the line between E and D? Because we just know that HPE are collinear.
Yeah, so maybe hide that. Yeah, so we know H, P, and E are collinear, and we know H, D, and Q are collinear, but we need to show that all five are collinear. BD intersect CE. Yes. Maybe I'll rename it just so we don't think it's the in-center. All right. AJ, let's let it meet the circle. Let me just hide this for now. It suffices to show G, I, and F are collinear. So basically, yeah, obviously I don't think, yeah, it doesn't pass through E. So, yeah, this looks very similar to the other problem we did. Then we can project through A onto BC. So, but GI and F are collinear because basically that's a true statement because let me draw this point. I think it's not drawing it just because there's there we go.
Can you move a little?
Or move
to see if collinearity correct.
Yeah.
Can you move A? Can you move A?
Oh, move A.
It seems true.
Yeah, no, it is true. GI and F are collinear because basically B, C, M, and H are harmonic. So if you project through A onto the circle, G, B, I, C is harmonic. So GI has to pass through F. So yeah, that's a true statement. So how do we from there prove that H, P, E, D, and Q are all? Oh, we don't know they're harmonic. You're right. Maybe there's another way to, let's see. No, you're right about that. Okay, so how did we define G? I forgot already. What was our definition of G?
It's the intersection of PL with circle.
Okay. But P, I guess I'm kind of, how did we define P?
Wait, we know that P is on DE. Problem says that.
But if we know P
we
is on,
define differently. We
yeah,
define it differently.
yeah, I think we're getting confused with how we're defining things, because if we know P is on DE, then the problem's trivial. I guess we were, yeah. Now I'm confused. Maybe we let H be the intersection of DE and BC, and we call this P prime. So maybe we first defined H, then we defined G, and then we call this P prime. So wait, does that work? I think that works. So it's kind of a little weird, but yeah, but okay. So basically, here's how we would do it. First, we would define H as the intersection of DE and BC. Then we would draw a point G, and then we would define a P prime this way. And then we would show P prime E and D are collinear. Does that work? It's weird, right? But I think it might work. Okay, yeah, I can define P as in the problem. So if I do that, then I have to show, so if I define P as in the problem, then it's not clear what point G is. Maybe I could define G to be Fi intersect the circle. G, oh yeah, okay. So we'd have D, E, P, and H are collinear. And then I guess D, E, okay, I think this works. Yeah. I got a little confused, but I think this should work. So we leave P as it was defined, and then so point L and K are defined, then we draw G, then we draw H. And then Pascal shows that D, E, P, and H are collinear. And then similarly, D, E, Q, and H are collinear. And oh, but wait, how do we know the G? So we let G be PL intersect the circle. We need to show that if QK intersects the circle at that same point, right? So PL intersects the circle at G. QK would intersect it at G prime. How do we know G equals G? Well, oh, I think, yeah, you can write your solution. So I think we could like use the converse of Pascal's, because once we know P lies on the line through H, E, and D, then Q lies on that same line. And so it's like the converse of Pascal's. You see what I mean? Okay, so hold on. I'm going to read what Hakan said again. So P, E, H, D, and Q are all collinear. I see why that's true. Once we know then GK has to pass through Q. Okay, yeah. Okay, so I'm going to write it up the way you said it. Sorry about that. Took me a little while to figure it out. All right. Make some room. Okay. So, yeah, do we even need point F? I don't even think we really need point F. Yeah, okay, yeah. Maybe I'll just copy your whole thing that you wrote.
Actually, Pascal directly shows this.
Pascal directly shows it?
The 5 points are collinear.
Oh, whoops.
Actually, 4.
Sorry, 1 second. Yeah, so it's kind of like he's using Pascal in reverse. Let's see how this looks. Hey, not bad. So okay, so GLC VBA, we have PE and H are collinear. So H, so those are all collinear. And then AGK BCC. So that means that, yeah, GK intersect the tangent, point D, and H are collinear. So this implies that PL and QK intersect on omega. I like this. PL and QK intersect. Yeah, Pascal's very slick. Pascal just cracks everything open. All right, so I'll go back to the one last problem that we didn't solve yet. So we have a half hour, and yeah, if we end up solving it, I could start looking for another problem. And if not, I'll leave it to the viewers. Okay, so a little messy diagram, but I feel like it's worth drawing those parallelograms because I feel like I've seen stuff like this before. You know what? I think it's worth drawing this point right here. Just because I feel like there's something special about point L, because triangle BLHC is similar to HBLC. Just looks super familiar. Are those parallelograms similar? I don't think so. But delete L for now, but I think it might be useful later. Let me check if we have isogonal lines. I don't think so, but it would be very cool if we did. No, 21 and 21.6. Yeah. So yeah, do we have any sort of spiral similarities? AH. So yeah, actually, let me draw that point L again. I know it seems kind of weird, but basically we'd have angle HCLC is, we want to show that's equal to angle AQH, right? So that's, wait, what did I do wrong there? Because this is perpendicular to this, and we want to show that that is perpendicular to that. So shouldn't, why doesn't that work? Oh, because I need to let HQ meet. Yeah. But, I mean, basically, I want to show that the angle between HQ and this is the same as this angle. So this is really awkward, but I'm basically, sorry, I'm going to undo this in just a sec. I want to show that this is a cyclic quadrilateral right here. Well, wait, hold on a sec. Doesn't seem right. This is tricky. I'm still thinking about trying to use the Pythagorean theorem. But yeah, I don't know how to get h be h squared. So yeah, we have a right angle here. I mean, yeah, actually it might help. If I draw this point, then it's collinear with h and q, right? Not necessarily, actually. Let's see, this is, I don't think that's true. Yeah, never mind. But it makes a right angle, so we have, if I let BC intersect this line at a point, I'd have a cyclic quadrilateral. So I have a really weird idea, and I know my ideas are kind of crazy, but basically, I want to draw the intersection right here. So we would have a cyclic quad. And AH, so if we draw the center of this circle, which is basically the midpoint of QL, then we draw the midpoint of AH, then we want to show that MN is parallel to HBHC. It's kind of weird, but and JN and K are collinear. So really random, weird configuration. If we could show MN is parallel to HBHC, That would solve it. Is there some kind of homophily? Because wait, I don't think HB necessarily lies on, yeah, QL. So we want to show MN is parallel to HBHC. Maybe we could like use the SARGs or something. I'm just throwing out totally random ideas here. Hmm. Let me go back a little bit to the where I drew the circle and yeah. So I mean, do we just want to show AHEHB? Well, no, we'd have to draw the intersection point. We want to show that cyclic. If I draw this intersection point, I want to show that that's a cyclic quadrilateral. I wonder if I could show like AHQ is similar to some. Basically, I think I want to show, if I draw this intersection point right here, I think I want to show AHQ is similar to HBLC. Is that right? I forgot how I, let me check that. That's 7.4. Yeah. And okay. Yeah, so I want to show AHQ is similar to HBLC. Sorry. So yeah, how would we? So first I could try to show angle AHQ is equal to angle HBLC. It's tricky. Well, wait a sec. I think because we know that this is cyclic. So angle AHQ, so angle AQH is equal to angle ECH. Yeah, so we know that those angles are equal. And yeah, we want to show that yeah, maybe we could somehow show that AQ over QH is HBC over CL. So HBC over CL, that's the same as BHC over BL. Which is the same as the sum of those two over BC. Guys, have any ideas? Let's see. Maybe you guys want to check out, like, so I don't think I'm going to open it up here, but maybe you guys could do, like, check out maybe complex numbers. I don't like complex numbers on my channel. But you guys could check out, there's this video, it's called like a brilliant polar chase on my channel. Maybe you could look at that video now and see if there's any ideas from it. Does it look similar to this? I'm curious. Two conflicting figure. Yeah, it's complicated, but I like parallelogram. We have two parallelograms like this. I feel like that's a useful thing. I could erase some of the, like maybe I could rephrase it. Like, so you have a point P, you draw the circumcircles of APB and APC, and then you draw the perpendicular to AP through A. And then you draw these parallelograms, and you want to show that. That's a little tricky. You found another link. Let me open it up. Let's see. Yes, exactly. And this was from the video that I think I referenced the same thing in that video, right? Is that where you found it? Sorry, let me go back. Yeah, he mentioned that in that session. So, oh, but I think we had to use. Oh, hold on one sec. Let's see. I think that other problem used the in-center though. I don't think we have isogonal conjugates. Yeah, so it looks pretty related, doesn't it? So you have the three orthocenters. So yeah, let's draw the isogonal conjugate of Q and then draw its pedal triangle. Okay, so I'm going to do that. Let's draw the isogonal conjugate of P. So I'm going to cheat just because I'm lazy. Here's how I'm going to draw the isogonal conjugate. It's actually probably, so I'm going to draw the pedal circle of P. And, oh, I wonder if L lies on that circle. I bet it does. So let me hide some things. But, okay, so this is the pedal circle of P. And it looks like it passes through L. And I think we proved something like that in that video. And once we prove that, I think that might help solve the problem once we prove that. If we use that fact. Oh, Hakan, did you just, oh no, it looks like someone else joined us. Hey, Furkan. Is, just curious, are you from Turkey? Just guessing from your name, but I'm not sure. All right, good. So yeah, we have about 7 more minutes here. And I noticed something. So L passes through the pedal circle of P. So if we knew that, and I think that's what the link shows, then Okay, let's say that was actually true. Would that help us solve the problem? So we want to show the angle between this and BC. I mean, yeah, we wanted to show angle HBLC was equal to angle AHQ. And if this were true, would it follow? I wonder if AH, yeah, it looks like these also intersect on the circle, which is interesting because we want to show AH is perpendicular to HBHC, but it looks like the two intersect on this circle. So that would mean like that AH passes through the antipode of L. So basically that means that that means that if PM and AH intersect on the circle, if we haven't proved, is that true? Yeah, PM and AH, let me make 100% sure, but that should be true, that PM and AH intersect on the circle, yes. Yeah, so there's a lot going on here. We only have 3 minutes left, so I don't think we're going to be able to finish it. But yeah, I think it's very related to that previous problem. Because once we know L lies on that circle, then angle HCLC, or angle MLS, but yeah, I still don't know. Yeah, we haven't used that Q lies on this circle, so I think there's still some work to do here. So we have PLM is similar to QLH, but we also need that PBQC is cyclic, which I don't think we've used. So this is a cool configuration. This is probably something worth remembering. Because yeah, there's a lot of interesting structure here. So I think I'm going to stop here because we're out of time. But for everyone watching on YouTube, thanks for listening. And thanks to everyone else who participated in this meeting. You all helped contributed a lot more to these solutions than I did probably. So if you like this video, give it a thumbs up and subscribe to my channel. And if you want to join my sessions in the future, feel free to email me at mgreen801@gmail.com. They're at 10 a.m. U.S. Central Time. So thanks, and see you all again.